Welcome all those who are on time. We still have a minute to go. So those who are watching the recording, I suggest that you skip the first minute or so because I will start sharp at 12:30. Today there might be less viewers, less participants because of that message going around that being a holiday there won't be any class. Well, when you are uh, in your home all these days, then every day is all these days are similar. But in case you are busy, you have to do some rituals, then the recording will be available. So Adit, Anushka Goyal, Abhinav Kumar, well, good afternoon. Very few today on time, but we will start now. As it is 12:30 now, so we will start. So we have seen in the previous class how to find the net electric field. And there is a purpose behind those activities that we were doing. We will utilize them to find the net force today. So we have done questions like these, the one on your screen, that there is a plus Q which is of 1 nanocoulomb, and there is another plus Q. Banshaj Raj Bhardwaj, good afternoon, kept along the x-axis, and this distance, if you remember, each of this grid is of 0.1 meter. So this is 0.5, this is 1 meter, and 1 meter away from it we are finding out how much is the electric field. So we calculated that, we found values, and we verified those values using this simulation, which is a free tool from Colorado University, popularly called FET simulations. We have done this. So we have done questions like this. We have done questions where the charges are kept along the say x-axis, and we found the electric field on the line joining the two. This also we have found out. At the center it is 0. We have also done this question that when you move on this perpendicular line, the electric field, the net electric field is in this direction as it is seen right now on your screen. Sorry. And it increases in value. But then it increases, and after a while it decreases. It decreases in value. That also we have seen. That when it is maximum, we have seen that a upon root 2 value, we verified that using this simulation that it was actually coming out to be a upon root 2. These things we have done. We have also done other few cases in which, say for example, there is a positive charge kept on one corner of the square, another positive charge kept on the opposite diagonal, and we found the electric field at the say the another corner of the square. This question also we have done, and we have seen if instead of any plus 1, if I put a minus charge, then what happens? See, right now due to this plus charge, the field at this point is towards right. The due to this plus charge, the field at this point is upwards. So you have to find out. Let me draw this thing and explain it a little bit better so that there is no confusion in your mind. A quick revision. So due to this positive charge, the field at this point is away from it and it is in this direction. Due to this, say if I'm calling this as charge number 1, so this is E1. Due to this charge, and if I call it charge number 2, then field due to it is in this direction, away from it at this point, and I'm calling it E2. Value-wise, magnitude-wise, E1 and E2 will be same, and so the net electric field will be the resultant, the vector resultant of these two, and that is what this electric field is showing. We have done these questions. Also, we have done a few variations of this question. Say, for example, if instead of 1 nanocoulomb, If we place 2 nanocoulomb, then what happens? And we have even found out, roughly we have found out what will this angle be. This 25.7 degree which it is showing from here, what will this angle be in that case? Also, we have done another case which we had a special interest in, that if instead of positive, if I place a negative, then what happens? Let me quickly revise this also with you, that what happens about the resultant and the magnitude and the direction. Due to this positive charge, the field is away from a positive charge, that is in this direction. And due to the negative charge, the field at this point is towards a negative charge, which is say down like this. So the net electric field because of these two is in this direction. There is a very popular form of this question in which these two charges are placed, say somewhere like this, and this becomes a dipole. And we have to find, this becomes an electric dipole. When it is plus q and minus q, it becomes an electric dipole. And we have found the net electric field on this. This is called the axial point, the axis of a dipole, axial point. We have found the electric field here. And we have found the electric field on the perpendicular bisector, which is called the equatorial point. And if you see that on this line, the field is parallel to the axis of the dipole. Parallel to the axis of the dipole. We have seen these things also. Now, how is that related to the questions we are going to do today? Our questions, our topic for today is the electrostatic force. Now, how is that related to today's topic? So let's say that there are two positive charges kept the way we were keeping it earlier, say like this. And if we find the net electric field here, which we have done earlier, so we can find the net electric field. Now, how were we finding this net electric field and how is it related to the topic today? Let me explain it a little bit. Due to this charge, at this point, we found the electric field and which was in this direction and we called it E1. And due to this charge, at this point, we found the electric field which was away from this positive charge. Away means it is in this direction. And that's how we were finding the net electric field. Now, if we place a charge here, let's say plus Q charge, we place it here. Then this charge, rather any charge, if a charge is placed at a position where the field is E. What do I mean by E? Due to this charge, the field is E1. So if you place a charge, that charge is going to experience a force given by Q into E. So if I multiply this expression, what was this E1? E1 was 1 upon 4 pi epsilon naught Q upon r square, where r is the distance between Q and this place. Say this position, say this is r. So r away from this positive charge, the field here was E1. Likewise, we can find expression for E2. Magnitude wise, E1 and E2, in this case, they are same because this distance is also r. And if this is plus 1 nanocoulomb, this one is also plus 1 nanocoulomb. So E1 and E2 magnitude wise, they are same. If you place a charge plus Q, a small q here, then the force on that charge is QE. So the force, instead of electric field, we can call this as F2 and this one we can call as F1. Force on that charge, this small q, which is placed here. And so the net force experienced by plus Q is the resultant of F1 and F2. And this expression means the vector resultant. Force is a vector quantity and the net force experienced by this charge will be the vector resultant of F1 and F2. Now, even though I expect that you people should be able to do it, but then let me quickly revise it for you. F1 and F2 perpendicular to each other, the net force, the magnitude of this net force is under root of F1 square plus F2 square, because the angle between F1 and F2 is 90. Otherwise, in general, it is A square plus B square plus 2AB cos of angle between A and B. Taking the under root of that, you get the net force. So if you know how to find the net electric field, finding out net force is just a matter of multiplying by Q. So all those questions which we did using these FET simulations to find out net field are being utilized to find out net force also. Abhinav Kumar, very good, root to F. Now what we are going to do is, instead of, so we will not be doing the basic questions which are given in the books on net force. I will show you those questions which are given in NCERT, which have been asked by CBSE. I will show you those, but the today's time we will spend more in doing some good questions, because remember, right, in class 1 I said, even though this class is CBSE NCERT based class, but I will certainly help you to do those questions which have been asked in the previous years in the medical entrance and engineering entrance exams. So that we will do. But before we move on to those questions, let me show you this activity that I have set up for you. Remember, somebody asked me what is a pith ball, and if you are able to see somewhere, there are three spherical kind of things that you are seeing in the frame right now, other than my face. If you consider my face to be even a little bit spherical, you see something hanging here, very small. I'll bring the camera closer to it. There is something here which are little bit bigger, and there is something in orange color there. These lighter things is what you say pith balls. Not exactly pith balls, but then they work like pith balls. How I have made them? You have those styrofoam balls, which you popularly call thermocol balls, very light balls. I have wrapped them up by the foil, the tin foil, the aluminium foil, which you use in kitchen to pack rotis. I have wrapped it with them, and because those styrofoam balls, you can pierce them with a needle. So I have passed that thread into them, and I have hung them using a pencil above. And now what I'm going to do is, and later on what we will do is, we will do numerical problems based on it from the book by H.C. Verma. But let's do this activity first. Now this, let me show you, and then we will discuss. Look carefully, because when I do it the second time, there will be something like a reset in this activity. Look at it. Running away. Now let me do it this side. Do you see that? Do you see that? Now I can do it again and again and again and again. Those effects which we have been talking about earlier, they are much easily seen with these balls. Why? Because they are very, very light. Very, very light. So what I'll do now is, the next that I do is, I'll touch both of them with the same straw and now see what they do with each other. Now do you see there's a gap between the two? They are not sticking together now. I'll do it again, but let me increase the size of the camera, the video part, so that you are able to see them properly. I'll do it again. See it with an increased size. Now let me do it again for you. The results will be a little bit different, and I'll tell you what, why, and what. Do you see the funny part happening now? Now let me touch them. Do you see this? Do you see this now, this drama? Because it was already charged. And now instead of getting attracted, it is repelling. So if I want to reset it, what I'll have to do, I taught you that thing in class 1, the first class or second class. I'll have to remove my shoes and touch these balls. Do you see the repulsion between the two? Now they are not willing to come together. Do you see that even in this camera, you can see that gap between these two? Today we are going to do numerical problems based on exactly this situation that you see right now above this in this video. I hope this is very much visible. Yeah, because even if they are, because they keep on turning around, but at some angle you are able to see that significant gap between the two, that they are not willing to come together now. Yeah, Binav, I have already taken care of your request. I have increased the size, and yeah, and your answer for earthing is also correct. So if I want to reset everything, I'll have to remove my shoes and touch these spheres so that everything becomes neutral, and then I will be able to do it fresh. But right now, otherwise, they will, till the time the charge gets leaked out, these two metal balls will be away from each other. These are called pith balls, light balls, so that their weight does not matter. You are able to see the electrostatic phenomena, very light balls hung with a long thread, light thread. This thread is even larger than this, so that the effects are easily observable. So now what we will do is, we will do few questions based on it. Allow it to hang like this. Let's see how long can they repel each other, and they continue to repel each other. So I'll reduce the size of the video, this window, and we will move on to numerical problems. And these questions are from H.C. Verma. The first one is a simple one, that from a point there are two metal balls. Each of these will have a mass m, and they are given similar charge. Let's say both of them are given plus q plus q. Both of them are having mass m and mass m. This is a usual case that you will see, and the kind that you are seeing in the video even now, that they are not touching each other, they are separated, a little bit separated. I charge them similarly by touching them with the same straw. So this is a usual thing that you will see. Now, if you put them on a table, then gravity's role goes off. And so on a table, the situation would be on a table that I won't be able to show you here, that this is the point of suspension. This thing is repelled. This thing is repelled away because there is that force, electrostatic force between the two. There is electrostatic force. The gravity does not play a role. Or what you can do is, I'll change the color and I'll draw that also so that it doesn't trouble you. This gravity is taken care of by the normal reaction of the table. This weight is taken care of by the normal reaction by the table. And this length, if the length of the string is L, then this is L and this is L. So the gap between these two balls is 2L. So look at any of this charge. Free body diagram of any charge, of any Q, any one Q. What do you get? There is, on the right you have electrostatic force, and on the left you have the tension on the string. And so if this charge remains at rest, well, there are these two also. There are these two also, but then if we consider the forces along the horizontal direction, then T is balancing it out, Fe. So question number 22 from H.C. Verma. Let me check. Sorry, question number 21. Question number 21 from H.C. Verma. says find T. Find T. So if you equate these forces, then T is equal to 1 upon 4 pi epsilon naught, both of them having same charge, and the separation between them is 2L, that R square. So this T is equal to this. That's the simplest. Now let's move on to the next question now. Next question from H.C. Verma, and that would be question number 22. And now we have two something like this. Same. I have not been able to draw them equal, but same. So there, if you consider any one of them, it has weight mg, and it has electrostatic force between the two. These separations have been given. These separations have been given. So what I'm doing is, this separation is given and they say it has been released. I will discuss it in my own way. I'm a little bit modifying. Take interest in it, because similar kind of questions are a lot of similar kind of questions are asked. And today's class, we are not going to do those simple ones, which we have actually done in the name of electric field. We will spend more time in doing questions like these. So let's say this is the tension T, and if this angle is theta, then this angle is also theta. So this side you get T cos theta, this side you get T sin theta, and this separation between the two, if this is the length L, let's say this separation is a 2a. For the sake of simplicity, in case I need the half of this, I can use A, because A upon L will give me something like sin theta in these diagrams, those kind of things. So I'm taking this distance to be 2. Or in case these things confuse you, I can work with only A, and if I need half of the distance, then I will use A by 2. Okay, now equilibrium. Equilibrium. Now the issue comes. Is there an equilibrium? Equilibrium or not? Is there an equilibrium or not? Well, the question that we are doing, question number 22, it says they are released from a distance of 5 centimeter, and after that it doesn't talk about whether there is an equilibrium or not. This is one thing that I like in the book by H.C. Verma, that it leaves the situation open. It doesn't allow you, it doesn't permit you to make a lot of assumptions. So I'll go step by step. It says that instead of these directions, draw the forces acting on it along the string and perpendicular to the string. Say these are the forces acting, mg, fe, and there is this tension T. This is the angle theta, same as this one. This is the angle theta. And they say instead of horizontal vertical, draw it along and perpendicular to the string. Along and perpendicular to the string. Now, if that was theta, then this is also theta. So this is 90 minus theta, and so this is also theta. I'll quickly write whatever is obvious. Fe cos theta this side, and this is mg sin theta. Now the question for you. This is along the string, and this is perpendicular to the string. Now the question for you. And these are significantly good questions. Question number 1. Is mg sin theta equal to fe cos theta? Or rather, I can make it more obvious. When is it not? When is it not? When is it equal and when it is not equal? If it is a case of equilibrium, if it is given that this situation, whatever you are seeing, and this A has been mentioned at 5 centimeter in this question, if it says that at a distance of 5 centimeter there is an equilibrium, then mg sin theta and fe cos theta, they are equal. But it doesn't say so. When it is, I say, if given equilibrium, if this thing is given. But if it is not given that it is equilibrium, then these two are not equal. Then in that case, if not, then mg sin theta minus fe cos theta represents what? It represents a force which will try to bring it back. So there is a chance of oscillation happening. Whether that oscillation is simple harmonic or not is a very different question. So right now, right in the beginning, let me warn you and let me take you back to few more things. In the NCERT and CBSE, these are the questions which have been given, and we have bypassed them by telling you clearly that we have done similar kind of questions in the name of electrostatic field. If you multiply the field by Q, you get charge. Oh, sorry, you multiply by charge, you get the electrostatic force. So these kind of questions which are in NCERT, these kind of questions we have done. So what I have done is, for today's class, I have moved on to little bit better quality of questions. Okay. And so this is what we are doing, and these are the questions taken from H.C. Verma. So mg sin theta fe cos theta can be equal when it is given that they are in equilibrium. Now even more interesting question comes now, and that is, be very careful to answer this question. There is a bright chance of you doing something foolish. Is t equal to this side, it is mg cos theta. Mg, we have taken two components, sin theta and mg. Is t equal to mg cos theta? Same thing that I am asking. When it is true, when is it not? Same kind of thing. Will anybody like to answer this thing? I'm giving you few seconds time. Is t equal to mg cos theta? When is it and when is it not? Can there be any situation where t is equal to mg cos theta? Can there be any situation when t is equal to mg cos theta? This t can be equal to mg cos theta can be if m is at rest, or say it is the extreme position. Fe sin theta. Fe sin theta. Oh, good. I have missed out this thing. 3 days grace. Thank you so much. Much sharper. Mg cos theta plus Fe sin theta. Okay. Good. I'm impressed. 3 days grace. Very good. Abhinav Kumar, every time it is true? No. If it is, say for example, it is oscillating and it is not the extreme condition, then T minus both these two forces. Just a minute, let me put it here, somewhere here, or let me write it here, because I don't need this space. If I go 2 down, then this diagram won't be possible, won't be visible. T minus F E sin theta minus mg cos theta is the net force inwards. Now, what is it equal to? This is equal to mv square by r in general. If it is going in that vertical circle, in that circle, then this net force inside is equal to mv square by r. Abhinav Kumar, am I able to help you recall what you have learned earlier? This net force inverse is in general equal to mv square upon r. But if it is an extreme position, then v is equal to 0. In that case, this whole thing is equal to 0 and t is equal to fe sine theta plus mg cos theta. Have I been able to clarify this thing to you? Okay, after this, the remaining things become simple. Remaining things, they become simple. If equilibrium, you will realize this is very easy case. Then this is very easy case. If there is an equilibrium given, then situation is anyway very simple. Why? You can simply equate these things, that you can say t sine theta is equal to fe and t cos theta is equal to mg. And understood, sir? I missed. Oh, that's perfectly fine. You are learning. And you saw even I missed out one point, which 3 days grace pointed it out. So if it is equilibrium, then it is very simple. T sine theta equal to Fe, and Fe is equal to 1 upon 4 pi epsilon naught Q square upon, if you are taking that separation as A, this separation as A, then A square. And if this A or A by 2 and L they are given, then sine theta cos theta also can be found out. And that is one of the questions in HC1. What I want to discuss with you in slightly the little time that we have is a question. If you place the whole setup in medium means you put the whole thing in oil, you put the whole thing in water, those kind of thing, then how does it matter? First thing is Fe changes. Then it becomes a good question. Fe changes. How does Fe changes? Instead of 1 upon 4 pi epsilon naught q square upon a square, it becomes 1 upon 4 pi. Wherever you have epsilon naught, you multiply epsilon naught by k, which is an electrical property of this medium called dielectric constant. Or it is called even epsilon r. K can be written there, or k, or it might be epsilon r given. Both of them. Yeah, there is another one also. But yes. Abhinav, that band force will also be there. I'll come to it. Any of these two which is given, relative permittivity or dielectric constant, both of them are electrical properties of the medium, and wherever in the expression, whether it comes in the numerator or denominator, wherever you get epsilon naught, you multiply that epsilon naught by that k, so Fe changes. But then second thing that happens is that there is a buoyant force which you have already got, and that buoyant force will be upwards. So instead of just mg down, there will be mg minus buoyant force. And so now you see that t sine theta is equal to 1 upon 4 pi k epsilon naught q square upon a square, and t cos theta balances not just mg but minus buoyant force. And buoyant force, if the mass or density of the volume or all those kind of things are given, then this is basically weight of liquid displaced. So in one of the questions in HC Verma, two things have changed. When you place the medium, two things have changed. The K has changed, the medium has changed. See, it is placed in the medium, so electric force is changed and buoyant force also applies, and they say theta remains the same. And so you might be asked to find out how much is the dielectric constant on all those type of things. So in today's class, what we have done is we have seen one activity. By the way, now the charge has been lost and they are in touch with each other. If you can see these two balls, you see these two, they are now touching each other. But it has lost. Gradually, the charge is lost to the surrounding air. It leaks out to the surrounding air. But we can repeat the same activity, or you can repeat the video, or you can do it yourself also. You have a lot of time nowadays. You can do that also. So in today's class, what we have done other than this activity, we utilized that knowledge which we attained in finding net electric field due to point charges, and we left those questions because they are very, very similar. Finding net force or finding net field, they are very, very similar. In net force, you put a place a charge q also. And so instead of finding field at that point, you start finding force at that point. Only difference is you multiply by a charge q. F is equal to QE. So those questions we left, but we came to questions which were utilizing these two pith balls. And we have done certain number of questions. Somebody has joined the class just now. So we took some questions from H.C. Verma, and we took this special case where two light, or say two charged balls, two balls are suspended by two threads. And in most of the questions, they say they are charged. The questions that we took, they are charged and they repel each other. But in one of the questions in H.C. Verma, the initially that you will have to go through, and I will mention you which question is that. Initially, they are suspended at a distance of 5 centimeter. But then what happens is they come somewhere here. They come somewhere here. And this distance is given to be 3 centimeter. Now, if you can understand the language of the question and you can draw the diagram, you can easily understand that in this case, the charges are opposite. It must be Q and minus Q kind of thing. Because they were hanging, suspended 5 centimeter apart, but now in equilibrium, they are 3 centimeter apart. Other things, they remain the same. Do remain in touch through the Telegram group or otherwise. And if you find any difficulty in doing these questions, do let me know. But I'm very sure those who have attended this class will be able to do these kind of questions also. If you have joined late, we have done few questions from H.C. Verma in today's class in finding out net force, or say equilibrium or not equilibrium, when there is an electrostatic force also between two bodies. See you again on Saturday, same time 12:30, and continue to remain in touch, continue to work hard. May God bless your hard work. See you again on Saturday at 12:30. Thank you so much.